Hello, welcome to Math 361, Statistical Methods 1. This is the Week 9 online video lecture covering the concept of correlation. So to talk about correlation, we're going to consider the following data set of fuel efficiency and 10 other measurements for 32 different vehicles from the 1972-1973 model year. Now that seems like a weird year to choose. That's because there is a data set built into R, the Motor Trend car road test data set, that includes this data from that year, 1973-1974. So we see here from the online description that the data set's titled MT Cars and will include 32 observations on 11 numeric variables. We'll be focusing on the fuel efficiency in miles per gallon and the weight in thousands of pounds. So once again, to use a built-in data set in R, we're going to use the data command, and then inside we have to put the name of the data set, MTCars. And that brings in an MTCars variable into our environment. If we want to see what exactly that looks like, we do head of MTCars. We're going to see the first 6 rows of data here. So like I said, we'll be focused on miles per gallon here, the first column, and then a weight in thousands of pounds. That is the 6th column here. And the question we want to answer is whether or not there's an association between fuel efficiency and vehicle weight. So the idea here is we are, for each object in our sample, we are making a multitude of measurements. We want to compare those measurements. So the best way to start this analysis is to visualize the data we're concerned with. And this will introduce a new type of visualization, a scatter plot. So we'll go into R here. Now to make these plots, I'm going to use a new plotting utility called ggplot2. This is a little bit more advanced than the default one I usually use. It's part of a package called the Tidyverse, which is used for data science tasks within the R ecosystem. So I'll load that library, and what I want to do is I want to make a scatter plot of just the 2 variables we're interested in here. So the command to do that, ggplot, tell it what data I want to use, MTCars. Now, this is based on notion of aesthetics. So here, there's an AES command, and I'm going to tell it what my X and Y variables are. So X is weight, WT. I see that's the correct variable name from the header up here. My Y variable will be MPG. And then I'm going to add some points for each of those data values. Let's see what we get out of this. So over on the right here, you see I have a scatter plot. I now get this gray background with grid lines. Along the x-axis, I have weight. Along the y-axis, I have miles per gallon. If I want to make this a little bit better, I can add some labels. Let's see, X, we'll call that weight in thousands of pounds. The Y label is fuel efficiency, MPG. And we give a title of fuel efficiency versus vehicle weight. There we go, a little better. So note here, just by looking at this quick scatter plot, we see a little bit of the relationship between fuel efficiency and vehicle weight. As vehicle weight increases along the horizontal axis, we see that fuel efficiency seems to decrease. And so before we get into this analysis too much, I want to talk a little bit about how we can qualitatively describe what we see in a scatter plot. All right, so back to the slides. How can we describe a scatter plot? Well, the first is we can talk about the direction of the scatter plot. If we focus on the horizontal axis, as the x variable increases, if the y variable increases as well, we have a positive direction. Now, like the data set we just saw, we could also have a negative direction. That would be when my x-axis variable increases, my y-axis variable decreases. And finally, the other option is that we have no real discernible direction whatsoever. In addition to direction, we can talk about shape or form of a scatter plot. The first one is the one we'll be focusing on in this course, and is a linear shape, where you could almost imagine drawing a straight line through your cloud of data points, and that straight line looking like a good fit for the data points. But we can also have other shapes. The middle picture here is that of a quadratic shape. Looks like an upside down parabola. And then the graph on the right looks like an exponential shape there, where it starts very low and then it starts to increase very rapidly. As the x variable increases, the y variable increases even more. So we have direction, form, strength. Now we can discuss. Here we have them in quotes because we're going to have to quantify what we mean by strength here. But we can imagine a strong strength here, where most of the points lie closely grouped together to form whatever shape they're making, versus on the right, a very kind of weak scatter plot where there still looks like there's a positive direction there and maybe a linear shape, but it's fairly weak because of how spread out the points are. So those are the main things we discuss: direction, shape, strength. A final thing we should be on the lookout for anytime we see any unusual features, such as outliers here on the left. That big point in blue is going to drastically affect our analysis going forward, versus on the right, where we might have something that looks like no real pattern, but it might be because we've actually got too much data here. We've got subgroups showing up in our display, and what we might really want to do is to break this data set up into smaller data sets and analyze each subgroup separately. So when we talk about quantifying the strength that we see in a scatter plot, we're going to focus mostly on the notion of correlation as it relates to measuring the strength of a linear association between two quantitative variables. So this would be a good measure to calculate when we see that the shape of a scatter plot is linear. Now, even in the other cases where the shape of the scatter plot might be quadratic or exponential, I still can calculate correlation, as we're going to talk about it here, but in those scenarios, the number I get is meaningless in the analysis. Now, a key feature of correlation as it comes to measuring the strength of a linear association is that this measure should not depend on units. We're focusing here on miles per gallon and weight in thousands of pounds. Now, if I were to change the units on the y-axis from miles per gallon to kilometers per liter, I don't want my measure of strength to change as well. So in other words, when we talk about how to come up with this measure, we can look not at the original units, but at standardized units. So here you see I have a coordinate plane where my x-axis is now labeled z sub x. So those will be the standardized x coordinates, found as usual by taking each x coordinate, subtracting off the mean of all x coordinates, and dividing by the standard deviation. And my vertical axis is z sub y. So those would be the standardized y coordinates. And I want to focus here on the first and third quadrants. Note here in these quadrants, both z sub x and z sub y will have the same sign. In the first quadrant, both standardized coordinates are positive, and in the third quadrant, both standardized coordinates are negative. The important part of this is that since they're the same sign, if we multiply the two standardized coordinates together, we will get a positive quantity. And note that when we have a positive linear association between two variables, most of the data points, at least their standardized versions, will fall into this first and third quadrant. Now, a few may linger over in the second and fourth quadrants, but the majority of the time, when we're multiplying the standardized coordinates together, we're going to be getting positive quantities. Now contrast that with the second and fourth quadrant, where in these quadrants the standardized coordinates will have different signs. In quadrant 2, z sub x is negative while z sub y is positive, and vice versa in quadrant 4. So in these quadrants, when we multiply the standardized coordinates together, we'll get a quantity that's actually less than 0. And these are the two quadrants associated with a negative linear association between two quantitative variables here. So all of this is motivation for this definition here of the correlation coefficient, which we label as lowercase r. Note that it involves z sub x and z sub y, standardized coordinates that have no units, and then n, the sample size, which also has no units. So r is by definition unitless. Further note that in the numerator we have the product of the standardized coordinates. So as I sum this up over all data points, this quantity should be greater than 0 if there's a positive association. However, if there's a negative association, most of those products will be negative, and so when I sum them all up over all data points, I should get a numerator that is less than 0. So I see here that the sign of r could be positive or negative, and that sign should dictate then the direction of the association. Also note the denominator has an n minus 1. That's similar to the formula for sample variance, once again because we have lost a single degree of freedom. So some facts about correlation. The sign gives the direction of association. It's between -1 and +1. That's unproven here, but we'll see later on where that comes from. X and Y are treated symmetrically, meaning that it doesn't matter if I put miles per gallon on the x-axis or the y-axis, my correlation coefficient R should be the same. Once again, there are no units involved in R, and it's unaffected by changes in the center or scale of either variable. And we must remember that it measures linear association, right? If I look at a scatter plot and I see that the shape of the scatter plot is quadratic or exponential or periodic, I could go and calculate this quantity, but it's going to have no meaning. I only assign it meaning when I see that the shape of the scatter plot is linear. And finally, it is sensitive to outliers. So we should be very aware if we see an outlier that either has a very large or small x coordinate compared to the rest of the data, or a very large or small y coordinate compared to the rest of the data, we should be very careful to investigate the true nature of that point and whether or not we want to include it. Occasionally we will actually calculate two correlation coefficients, one with the suspected outliers and one without the suspected outliers. So if we go back to R, to calculate the correlation coefficient, I'm going to type question mark COR, and we see here in the help I get correlation, variance, and covariance. We did not talk about covariance in our class. That's another approach for defining the correlation coefficient. We could talk about covariances instead of using standardized coordinates, but we're going to focus just on standardized coordinates. So I want correlation, X and Y. We'll add two data sets there, and by default the method it uses is Pearson. That's the formula we just defined. So I want to do correlation here, COR, and now I have to get the data. So MT cars along the x-axis I had weight, and MT cars along the y-axis I had MPG. So I see here the correlation coefficient is approximately -0.867. So the negative sign means that I have a negative linear association. And the fact that this number is fairly close to -1 means that it's a fairly strong negative association. Now that I've seen that, what I may want to do is then go and see if I can find a model that explains this linear association between these two variables. We'll be talking about that in class next week when we find lines of best fit. So finally, I want to bring up a common point of confusion, that correlation does not equal causation. Just because we see a strong correlation between vehicle weight and fuel efficiency does not mean that vehicle weight causes a decrease in fuel efficiency. A famous example of this is shown on this graph here. It's the population of a town in Germany at year's end versus the number of storks observed each year. Along the x-axis is the number of storks, along the y-axis is the population in thousands. And note here, there appears to be a fairly strong positive linear association. The more storks there are, the larger the population. So one might erroneously decide that an increase in storks causes an increase in population. That seems reasonable because storks carry babies with them as they come to a town. Now, of course, that's not true. And in fact, if you were even going to consider an example of causation here, you'd probably want to look the other direction, because there are other variables we haven't taken into account here. In particular, as population rises, we need more buildings, more houses, which requires more chimneys, which then provides more opportunity for storks to find a place to land and build a nest. So just because we calculate a strong correlation of, say, 0.9 or -0.86 does not indicate a causal relationship between the two variables. That's a separate topic for another course. So in summary, correlation measures the strength of the linear association between two quantitative variables. I could calculate this quantity for any pair of quantitative variables, but it only has meaning if I see that the association appears to be linear in shape. The correlation coefficient R is a unitless quantity between -1 and +1 whose magnitude quantifies the strength of linear association and whose sign gives the direction of association. And finally, correlation does not imply causation. See you in class on Saturday.